All right, next up we have diffusion and Graham's law. Graham's law of diffusion or Graham's law of effusion as well. So we have two different things. We'll focus primarily on diffusion in this class. So diffusion, if you recall, is the movement of a substance from where there's a lot to where there's not a lot. So it says the spontaneous spreading and mixing of a gas or liquid particles. We can see an example of this on the bottom of page 464. We'll start there. We have some bromine liquid that you put in a container, and it's going to evaporate, and those gas particles are going to spread out and occupy the entire volume of that container. Top of page 465, we have some helium in the container on the left. The valve is closed. If you open the valve, the gas is going to move from left to right, from where there's not a lot to where, from where there is a lot to where there's not a lot. Eventually, you're going to have equal amounts of helium gas on both sides. We see that with nitrogen as well, but just below that, doesn't matter what the gas is, it's going to move from where there's a lot to where there's not a lot. And how fast this occurs depends on a couple things. Depends on temperature, first of all. This is not in the notes. But at a higher temperature, of course, particles are moving faster, and therefore a gas will diffuse and effuse faster at higher temperatures. But if we're talking about, let's say, different gases at the same temperature, how fast they diffuse depends on their relative masses. So we've talked about this before. The relationship between mass and velocity works for diffusion as well. Says at the same temperature, less massive particles move faster than heavier particles, therefore will diffuse faster. Take a look at the bottom of page 465. On the left side of that tube is introduced some HCl gas, left side HCl, and on the right side is NH3. And when HCl and NH3 combine, they form ammonium chloride solid, which is a white solid. And so what we see is we see a ring of ammonium chloride. It's kind of hard to tell, but look very closely. We see whites, kind of a white spot there towards the middle, not quite in the middle. Notice that the ring is closer to the HCl than it is the NH3. Why is this? It has nothing to do with pressure or anything like that. It has to do with the fact that the HCl molecule, which has a mass of about 36 AMU, is heavier than the NH3 molecule, which has a mass of about 17 AMU. So given that the ammonia molecule is lighter, it's able to diffuse faster. So the HCl is going to move to the right, the NH3 is going to move to the left inside that tube. And because the NH3 is lighter, it's going to move faster, and those two substances will meet closer to the HCl and then the NH3 end. All right, so let's take a look at Graham's law. I'm going to derive it for you. And so I'll derive it the way I did in my other classes. So let's say we have two gases at the same temperature. So if they're at the same temperature, then their average kinetic energies are the same. So remember, kinetic energy is 1/2 mv squared. So I have m1 is the mass of one of the objects. v1 is the velocity of that object. m2, mass of the other object. v2, velocity of the other object. So let's simplify this a bit so we can get rid of the 1/2s. So we have m1 v1 squared equals m2 v2 squared. So I'm just going to rearrange it so that I have the velocities on the same side, both of them, and then the masses on the same side. So I'm going to divide both sides by m1, and I'm going to divide both sides by v2 squared. So v2 squared cancels there, m1 cancels here, and so we have v1 squared over v2 squared equals m2 over m1. One last step, and then we'll arrive at Graham's law. Let's take the square root of both sides. And so I'm going to write that over here. So what we get is v1 over v2 is equal to the square root of m2 over m1. Now be careful with that. Notice that's we kind of have inverses there. So velocity is the same thing as rate. So we can also write, say, rates of diffusion of gas 1 over rate of diffusion of gas 2 is equal to the square root of the ratio of mass 2 to mass 1. So this is Graham's law of diffusion. Okay, so be careful with that. Let's take a look at some examples where we can apply this. An unknown noble gas diffuses 1.38 times faster than bromine gas. Remember that bromine is diatomic. Calculates the average atomic mass of the unknown. All right, so we're not given the rates of diffusion or the velocities, but we're given this factor here. So the unknown diffuses at a rate that's 1.38 times faster than bromine. And so what I'm going to do is this. I'm going to go 1.38 equals square root. So now be careful. Which number goes where? Bromine, Br2, has a mass of about 160, we'll say, AMU. And so which one is faster? Well, it says the unknown diffuses faster, so that means it is lighter. So, you don't have to do this, but, it's 1.38 over 1. And so what we're going to end up with then is with this. So this x corresponds to this 160 corresponds to this. So let's solve for x. So I'm going to square both sides. And so we end up with 1.38 squared equals 160 over x. Be careful about solving for x. You can just switch it with whatever's over there. Go ahead and pause the video and get that answer. And go ahead and answer letter B as well. So make sure this makes sense. Since the unknown noble gas is diffusing faster, it must have a lighter mass than bromine. Bromine's 160. Our answer has to be less than 160. So we get 84.0 AMU. What's noble gas has an average atomic mass of about 84, and that looks to be krypton. All right, so go ahead and try this one on your own. It says oxygen molecules have an average velocity of 482 meters per second at 25 degrees Celsius. The temperature here is irrelevant. Calculate the velocity of hydrogen molecules at this same temperature. Now let's predict the answer. How does the mass of a hydrogen molecule compare to the mass of an oxygen molecule? And knowing that, then what should the answer be compared to 482 meters per second? So make those predictions and then go ahead and set it up and see if your answer agrees with your prediction. Go ahead and pause the video now. Now notice how I set it up here. You may have set it up differently. Maybe you did 482 meters per second over V, whatever you want to call that, V hydrogen. And then if you did that, then it's going to be 32. Remember, oxygen is O2 over 2.02. If you do that, it's just a little bit harder to solve for V. So I wanted to solve for nice and easy. So take the 2.02 divided by 32, square root that, multiply by 42, and you get 1,920 meters per second. Now, hopefully that agrees with your prediction. Hydrogen molecules being lighter should diffuse or move faster than the heavier oxygen molecules. All right, next up, let's look at the difference between ideal gases and real gases. Previous mathematical relationships between pressure, temperature, volume, and the number of particles to work, it had to be assumed that the gas particles occupy no space and exhibit no attractive forces. According to this criteria, the gas would be referred to as an ideal gas. So ideal gases, they have no volume and they exhibit no attractive forces. Under normal conditions of temperature and pressure, these assumptions, although inaccurate, allow one to calculate answers for pressure, temperature, volume, and number of particles that very nearly approach the real values. So Ideal gases have no volume, so that must mean real gases do have volume. So 1 mole of a real gas occupies slightly more volume than 1 mole of an ideal gas because the volume that real gas particles occupy. So real gases, the particles themselves have volume. Think of it this way, the distance between the particles of a real gas and ideal gas are the same. So if real gas particles take up space, then the distance between them is going to be the same, and overall that sample is going to have then a greater volume. Likewise, ideal gas particles exhibit no attractive forces, and because of this are able to travel in straight lines. This is going to affect the number of collisions between the particles and the walls of their container. Whereas real gas particles, because they exhibit attractive forces, this will cause their paths to curve and bend. So remember, the shortest distance between 2 points is a straight line. So that would be an ideal gas. Well, what if you have a real gas? Now, even though we have other gas particles in here, doesn't matter. Those gas particles are not attracted to each other. But what about this here? So this gas particle is attracted to that, and maybe it's attracted to this, and it's attracted to other gas particles, and so its path kind of bends and curves. And because of this, it's going to strike the walls of its container less frequently, resulting in a lower pressure. In summary, the volume of an ideal gas is less than the volume of a real gas, and the pressure of an ideal gas is greater than the pressure of a real gas. So let's look at some deviations from ideality, we call them. Larger molecules deviate more from ideal volume than smaller molecules. And molecules with strong intermolecular forces deviate more from ideal pressure than molecules with weak intermolecular forces. So a couple examples. Will H2O or H2S deviate more from ideal pressure? So since we're looking at ideal pressure, we want to look at intermolecular forces. So what type of intermolecular forces do water molecules and hydrogen sulfide molecules exhibit towards each other? So to determine that, we've got to draw good old Lewis structures. So Lewis structure for water, Lewis structure for hydrogen sulfide. Both are polar molecules. Water, though, exhibits hydrogen bonding. Hydrogen sulfide exhibits dipole-dipole forces. So in your explanation, you would write this. Because the hydrogen bonding in H2O is stronger than the dipole-dipole forces in H2S, H2O will deviate more from ideal pressure. All right, how about this one? Will methane, CH4, or ethane, C2H6, deviate more from ideal volume? So when we're looking at deviations from ideal volume, we want to look at the relative sizes of what we are comparing. So let's again take a look at Lewis structures or structural formulas. Methane structural formula looks like this. Ethane looks like this. So the answer is ethane. Because ethane has more atoms, so we're going to look at one of two things: the number of atoms in the molecules we're comparing, and the sizes of the atoms in the molecules we're comparing. So all the atoms in these two molecules are the same, but since ethane contains more atoms, it is a larger molecule. So your explanation is because ethane is a larger molecule than methane, ethane will deviate more from ideal volume. So this molecule here is just simply larger than the methane molecule, therefore deviates more from ideal volume. All right, changing gears a little bit, Avogadro's hypothesis, also known as Avogadro's principle. Not to be confused with Avogadro's law. Avogadro's law is that mathematical equation that shows the direct relationship between volume and moles. This one's a little different. Here's what it says. Equal volumes of different gases at the same conditions, so same temperature and pressure, contain equal amounts of moles. equal volumes contain equal moles, or what it says here in the notes as well. Equal moles means equal number of particles. So very, very, very important. So let's take a look at some examples. Two identical flasks, so same size, same volume, contain two different gases. One flask contains 3.03 grams of helium. How many grams of hydrogen can fit into the second flask at the same conditions? Well, equal volumes contain equal masses. I don't think that's what it is. Equal volumes contain equal moles. So let's do this. Let's take our 3.03 grams of helium and convert that to moles. Go ahead and do that now. Pause the video. So we get that this container can hold 0.758 moles of helium, or more importantly, any gas, including hydrogen. So the question is not how many moles of hydrogen can fit into that second flask that's the same size and at the same temperature and same pressure, but how many grams. So now we're going to take 0.758 moles of hydrogen and convert that to grams of hydrogen, and we'll get our answer. Go ahead and pause the video, punch that up. All right, so what'd you get? Should get 1.53 grams of hydrogen. Let's take a look at a different one. It says a flask was found to contain 5.06 grams of oxygen gas. Remember, oxygen is diatomic. This same flask was emptied and filled with an unknown gas that had a mass of 4.43 grams when measured at the same temperature and pressure. This time, what is the molar mass of the unknown gas? So I think this is the first time we've seen a problem like this. Molar mass of a substance. How do we determine the molar mass of a substance? Well, if we know what it is, we can use a periodic table, just like we did on the last example for both helium and hydrogen. But what if you don't know what it is? How do you determine the molar mass of an unknown substance? Think about the units for molar mass. They're not grams. The units are grams per, what does that per mean? Over, doesn't it? Grams per mole. And so we'll see this in several different contexts. Pretty simple. To determine the molar mass, mm, I write it here, we take the mass of the substance, m for mass, and divide it by the abbreviation for moles, actually is not abbreviation, but rather symbol, not abbreviation, is n. So we get mass of the substance, which I'm pretty sure we're given, divided by moles of the substance, which we need to calculate, and that will give us the molar mass. All right, so question is, how many moles are there? Well, we apply Avogadro's principle. Equal volumes of different gases contain equal moles. So however many moles of oxygen can fit in the container is equal to the number of moles of the unknown gas that can fit into the container. So go ahead and punch this up and see what you get. Pause the video now. So we get 0.158 moles of oxygen, or again, more importantly, this is moles of the unknown gas that can fit in the container. So we know grams of the unknown. We now know moles of the unknown, which, by the way, you can do this. You don't have to do this in 2 steps. I'm just showing you just to walk you through it. But we could have just done something like this, where we put the 4.43 grams on top of all of this and got our answer. Here I'm just showing you 2 steps. Take the grams divided by the moles and we get the molar mass. Go ahead and punch that up. And you get 28.0 grams per mole. Second part of the question, what diatomic molecule might this be? So which of the Hofbrinkels has a molar mass of about 28 grams per mole? And it looks like this gas could be nitrogen gas, N2. All right, that concludes this lesson. Thanks for watching.